Hi, everybody. Welcome back to week number 5. This is Mr. Harfiness and Miss O'Reilly bringing you a lesson on writing electron configurations. We're going to take what we did last week and we're going to go a little bit more in depth, and hopefully you'll walk away with a better understanding.
And even before we talk about what we did last week, we're going to backtrack even a little bit more and talk about light. So we talked about light a couple of weeks ago, and we talked about its dual nature, how it can act as a wave and a particle. Turns out matter can act the same way. So matter waves refers to the wave-like behavior of matter. And this was first hypothesized by Louis de Broglie and later confirmed by the scientists in Bell Labs in New Jersey. They noticed that electrons reflected off of metal surfaces and created patterns very similar to those that X-rays produced. And de Broglie's equation had predicted the exact pattern. So why do we care about matter waves? The uncertainty principle is related to this, and it's based off of this. The uncertainty principle states that the momentum, which is this essentially the speed, and the position of an object, in our case, the object is an electron, it cannot be simultaneously measured and known exactly. So why is that? Well, let's think about finding something in the dark. If you look in the dark for something, you need a flashlight. And that flashlight, the photons that are emitted from the flashlight will bounce off of the object and come back to you before you can even see it. So why can't we do this with an electron? Why can't the photons bounce off the electrons, come back to our eyes, and then we can see where the electron is? Or come back to the instrument in our case, because we wouldn't be able to see it with just our eyes. Well, the electron is so small. When the photon hits the electron moves to a different position. So by the time that photon comes back to our eye or to the instrument, the electron is now in a different place. So we can't actually be sure of where it's going to be. And that's why we call it the uncertainty principle, because we're uncertain about it.
And remember from last week also that when we were talking about orbitals, orbitals are the most likely places where an electron can be found. And that's why we're going to go an diagram with you. Okay, so this Venn diagram is going to kind of compare the two different types of diagrams that you might see. So the one on the left is called an orbital diagram. And that's where you're going to actually show each particular sublevel and the electrons in that sublevel. And it's a little bit more descriptive than regular electric configuration because it actually allows you to see the spin of the electron, which is the Pauli exclusion principle. And it also shows you, if you do it step by step, it'll show you that that Hund's rule is followed, that each sublevel is filled halfway before it's filled all the way. Then the electron configuration on the right for fluorine is just it tells you all you need to know, but it tells it more for a scientist who kind of already knows the location on the periodic table and knows the number of valence electrons, etc. But the idea here is that both the orbital diagrams and configurations show you the total number of electrons and are obeying the Aufbau principle.
So let's review those rules that we talked about last week. The first is the Aufbau principle. This says that energy levels fill with the lowest energy first. And we use this diagonal diagram to help us remember the order. Remember, you can also follow the yellow brick road on your periodic table to remember the order as well. The second rule is the Pauli exclusion principle. This says that only 2 electrons fit in each orbital, and those 2 electrons must have opposite spins. And we show that with arrows going in the opposite direction. So you see where they're in the same direction, that's the wrong example, and this bottom one is done correctly. The third rule is Hund's rule. This says that sublevels have as many unpaired electrons as possible. So instead of having them fill up, down, up, you're going to have them go up, up, up. And this is the correct way to do this.
So we're going to start to practice. We're going to do this together with you. It would be a good idea for you to have this written down in your notebook as we go through it. So as we look at sulfur's configuration, we're going to do both the orbital notation and the electron configuration. Remember, the first thing that you want to do is you want to look at your periodic table and find the element sulfur and look to find its atomic number. That atomic number is going to tell you the number of protons, but in the case of a neutral atom, the number of electrons. In this case, sulfur has 16 electrons. So as we go through this, if you look at the bottom right-hand part of the slide, you're going to see that we're going to follow all three rules. So the first thing that we're going to do is we're going to follow the alpha principle. And the first symbol that gets filled up is the 1s. And it has one orbital, and there will be 2 electrons in it. So we call it 1s2. Okay. The second, and you can see that they have opposite spins. The second sublevel is the 2s2. Again, there's only one orbital, and they're going to have 2 electrons in it that have opposite spins. Up next is the 2p. And remember, the p sublevel has 3 orbitals that could each hold 2 electrons. So as Miss O'Reilly is going to show you how to fill it up, you're going to see that it obeys Hund's rule. She's going to fill up 1 electron in each of the orbitals first, and then she's going to pair them off second, for a total of 6 electrons. Now, if you look at this top row already, we have 2 from the 1s, 2 electrons from the 2s, and 6 from the 2p, for a total of 10 electrons. We have 6 more to go, so we have to continue on the yellow brick road. So after the 2p6, the next sublevel is the 3s. And again, like all s sublevels, it has 1 orbital, and it's going to have 2 electrons in it. So now we're up to 12, so we have 4 electrons left. So we have to continue on. So we're going to draw out the 3p sublevel, just like the 2p is going to have 3 orbitals and different electrons in each of the orbitals. But we only need 4. So we're going to put in our 13th electron into the orbital on the left. We're going to put the 14th one in the middle. We're going to put the 15th one on the right. And so again, obey Hund's rule, we're going to then fill up the one on the left all the way for number 16. So this would be not 3p6, but it would be 3p4. And there you have it. 16 electrons, all taken care of, obeying all 3 rules. Okay, so as we're waiting for the screen to change, we're going to be doing a much longer one, lead. So if you go find lead on the periodic table, you're going to see that it's kind of on the right side. It's metal, and it's going to be number 82. Okay, so this time we're working about 82 electrons. So this is going to take a lot longer and take up more space. On a problem like this, electrons, it would be not time efficient to draw out the orbital notation. So we're just going to draw out the electron configuration. And keep in mind that if you go into higher levels of chemistry, there is also a shortcut that can be done with this too. But we're not going to go over the shortcut today, okay? So we're going to start. And it's important that we kind of keep track of our electrons, okay? So we're going to start with the 1s2 sublevel. Okay, then we're going to go, following our yellow brick road, we're going to go to the 2s2. You could already know there's going to be a lot because there's 82 of them. Okay, so after 2s2 comes 2p6. So we've taken care of 10 electrons. We have 72 to go. Then we're going to go to the 3s2. And then following the 3s2 should be 3p6. And then continuing on, we have the 4s2. If you add up all these electrons, you'll notice by now that we're at number 20. So we have quite a ways to go. Continuing on, we're going to now go to the 3d sublevel. So there's going to be 10 electrons because remember the d sublevel has 5 orbitals that can each hold 2 electrons. After the 3d, we're going to go to 4p6. And then after 4p6, we're going to go to 5s2. Okay. And if we continue to count, you probably notice that we're about 38 electrons. So we still have a long way to go, Miss O'Reilly. After 5s comes 4d, 10. And then followed by 5p6. And then we are getting closer 6s2. Okay, and if you add up the electrons, we're about 56-ish. So we're getting there. Okay. After this, we're going to venture on down to the F block for the first time. This is a big one. And remember, the F sublevel is going to have 7 orbitals. So it's going to be 14 electrons. And I think we're in the lanthanide series right now, which Ms. O'Reilly is showing you. Okay, we are up to 70 electrons. And after the 4F comes to 5D, and just like the other Ds, it's going to hold 10. And we are getting close. We're at 80. So we're finally at the very end, because following the 5D is going to be the 6P. But we only need 2 electrons. We do not need 6. So it's going to be 6P2. So there you have a very long configuration for a very big element. But you shouldn't be scared to do any of them, because if you followed along with us, you can do this for any of the elements on the periodic table.
And in part B, we're going to be walking you through more practice with this. So don't feel like you have to be an expert right now. So if you have any questions, please feel free to reach out to us through Google Classroom or in our emails, and we'll be happy to answer them. But stay tuned for part B so that you guys can get some practice yourself.
Bye.
Bye. Have a great week.